with hexadecimal to binary. So similarly, like we did for the other ones, there are some steps we would have to follow, okay? So like the octal number system, the hexadecimal number system is also used mostly, okay? And for conversion, we will still have to convert it using 4-bit binary equivalents, okay? So the procedure is as follows. You first of all write the hexadecimal number. Then you write 4-bit binary equivalents for each of the hexadecimal digits, okay? Then you check if there are any zeros after that. If there are zeros on the left-hand side, you would drop off all those zeros until you reach where there is a 1, and then you write all that as the binary equivalent for that hexadecimal figure or value. So let's look at a quick example here. So when we take this hexadecimal value or number of 2d6 subtract 16, which means it's a hexadecimal. If we want to convert it to the binary equivalent, what we will do basically is that we will take each of the hexadecimal digits and represent it with a 4-bit binary equivalent. So when you take from the right, which is the LSB, to the left, which is the MSB, or LSD and MSD, for 6, we know that its binary equivalent is what? 0, 1, 1, 0, because here is 1, because this place will be 1, this place will be 2, this place will be 4, and this place will be what? 8. Okay, so basically, if that is the case, then it means that the 6, its equivalent in binary is 0, 1, 1, 0. Similarly for D, what is the value for D in hexadecimal? Any idea? Can someone remind us? So for hexadecimal, we say we start from 0, we get to 9, and then 10 is A, 11 is what?
The D is 13.
7 is B.
B is what?
13.
B will be 13. B is 11.
D is
B is
11.
13.
Is it 13 or 11?
D is 13.
13.
13.
Okay, so if D is 13, then it means we have 8 plus 4 plus 1, that is 13, right? And then 2, as usual, is 0, 1, 0, 0. So when you write all these down, what will happen is that because there are zeros preceding it, they are insignificant. So you can drop them off, and then eventually you get 1, 0, 0, sorry, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0 as your binary equivalent for the hexadecimal number 2d6. Please, is it clear? You can just give me thumbs up if you're okay, then I'll move on.
Okay.
All right. So basically, that is how to do the conversion from hexadecimal to binary. Similarly, we can also do the same conversion from binary to hexadecimal, okay? So what you do with binary to hexadecimal also is that you would write the binary number, and then you again start from the rightmost position, which is the LSD, which is the least significant digit, to the MSD, which is the most significant digit. Then you group the binary into 4 groups of 4 bits, or into groups of 4 bits. So you take the first 4 bits from the right, the next 4 bits from the right, and then if you are left with some bits and you don't have enough to make 4 bits, you just add zeros to them. Then we now convert each and every one of those 4 bits or those octets into a hexadecimal equivalent. Okay, so let's see if we have an example in that regard. So here is an example on how to convert a binary to hexadecimal. So we have 10111, and we are asked to convert it to its equivalent hexadecimal. So the first thing we do is that we write out all the binary digits, and then we start from the LSD, which is the rightmost position. We take the first 4 digits, and that will be 1101. That is if you are starting from the right. And then it means that we'll be left with only 1 digit. So in that case, we add 3 zeros to it. And then eventually, if we convert that binary into its hexadecimal equivalent, it would be 7. And then the other one would be what? 1. So at the end of the day, the binary equivalent, or the hexadecimal equivalent of binary 10111, is 17 underscript what? 16, or 17 to the base 16, which shows that it is a binary digit. Okay. Sorry, a hexadecimal number. Please, do we understand?
Yes, sir.
Okay. Now, let's move on to look at something we call BCD, or binary coded decimal. Now, the binary coded decimal is a way of expressing each decimal digit with a binary code. Okay. And since there are only 10 code groups in the BCD, or the binary coded decimal system, it is very easy to convert between decimal and binary coded decimals. So when you look at this table here, the table here gives decimal digits with their corresponding binary coded decimal numbers or values. Okay, so here the BCD system also has a name that we call the 8421 code, which is just a way of representing that if you are taking 4 bits of a binary digit from the rightmost position, which is assuming you are taking it, just 1 second, let me illustrate it for you. So assuming you're taking 4 binary digits, even if it is 0, 0, adding my writing, my stylus is not here, so I'm not getting it with precision, but let me see what I can do for you. So 0, 0, 0, 0. What we are basically saying here is that a BCD or a binary coded decimal is also called the 8421 code, which means that for each and every one of the digits in the 4-digit code, each of them has a decimal representation. So we have 8, 4, 2, 1. And basically, anytime there is a 1, then it means we'll look at the the decimal equivalent. So assuming I have, let's say, um, I have 5 as my decimal number. If I'm looking for its BCD, if I'm taking 8, 4, 2, 1, and I'm looking for 5, it means my 4 and 1 will give me 5. And then would have what? 0, 0 here. So you'd get, for 5, you would get 0, 1, 0, 1. Okay. So that is basically how the representation for the binary coded decimal is. So from this table, you see that you have the decimal digits from 0 to 9, and then you have its equivalent BCD also from what? 0 to 9. So if let's take from the first one, 0, 0, 0 means that all the bits are off. So technically, even though they are 8, we're looking at it as an 8421 code. Because we have 0, 0, 0, or because we have 0 here, everything will what? Be 0. Then when you move on to 1, when you look at the 8421 code, to get the equivalent of 1, it means we can only turn one of that code on. When you go to 2 as well, the same thing. And then when you come to 3, it means 2 and 1 can be on or turned on to give us what? The binary coded decimal equivalent of the decimal digit. Similarly for 4, 5, 6, 7, 8, and 9. So basically that is how we do the conversion from decimals to binary coded decimals. Okay. Please, do we understand?
Yes, sir.
Okay. All right. So when we move on, let's look at binary, the procedure which we just explained. If we are to convert a decimal number into a binary coded decimal, first of all, what we would do is to write down the digits of the decimal number. That is, in this case, we are looking at what? 35. So 3 and 5. And then we now convert each of the decimal digits into a 4-bit binary equivalent. And so 5 would give us 0, 1, 0, 1. Then 3 will give us 0, 0, 1, 1. So after writing it out to get 0, 0, 1, 1, 0, 1, 0, 1, because it starts with zeros, we would knock the zeros off, and then we can write our BCD as 1, 1, 0, 1, 0, 1. So basically, that is how we do conversion from the from decimal to binary coded decimal. Okay, so kindly take note of that. So at your leisure time, you can also decide to convert this. But if you want us to try the first one, it means that we would first of all have, just 1 second, let me activate the pen. So we'll first of all have 8, and then we'll have 4 and 3. So what do we do next? If we want to write the equivalent binary for 3, it will mean we would have 0, 0, 1, 1. Binary equivalent for 4 will be 0, 1, 0, 0. And then binary equivalent for 8 will be 1, 0, 0, 0. So at the end of the day, we're going to get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, B, C, D as a binary equivalent. Okay. And that will be our binary equivalent. Please, do you understand? Is it clear? Voila.
No, sir.
You want me
Sir,
to
there was a mistake in your answer.
where?
That in between the
second phase zeros.
Oh, I wrote 5 zeros instead
5
of 4.
zeros, yes.
Yes, thank you so much. So you should be very mindful of when you are writing the final answer so that you don't write more than it's supposed to be. Okay. Thanks for prompting me. The conversion was right, but when we're putting them together, I wrote more than that. That's fine. All right. So basically, that is how the conversion is supposed to be done. Okay. So take note of that. Determination of a decimal number from a BCD number. So similarly, we can also determine a decimal number from a binary coded division number. And the steps are as follows. You first of all write the BCD number, and then from the rightmost hand side, you break the code into groups of what? 4 bits. You can also add zeros at the left position if the bits that are left are not up to the 4 bits. And then you convert each of the 4 bits to its equivalent what? Decimal digit. And then when you are done, you write them together. So let's see if we also have an example for that. So here, to determine, let's illustrate the procedure by considering the BCD number 1101010001. So here, you would notice that the BCD has been converted into what? 4 octets. That is, you have the first one, which is 1000, which is the first set. Then you have 1010, which is the next set. Then you have 11. But because it's not up to 4, 2 zeros have been added. And that makes it what? 4 binary digits. And then when you convert each of them, the first one gives us 1, the second one gives us 5, and then the last one gives us what? 3. But when you are writing them together, you can decide to drop off the zeros. Sorry, in this case, we don't even need to rewrite the zeros. We are only using the decimal digits. So you write 3, 5, 1 to the base what? 10. Or if you don't add any base, it is seen automatically as a decimal number. Okay. Give me 1 second. Okay, let's continue. So these are some examples for you to try your hands on, okay? Let's see if we can try our hands on the first one or the very first one. So the first one we have so if we take the first one, we have the first 4. We have the first 4 bits, which is this one. And then we have the next 4 bits, which is this one. And then we have the next 4 bits, which is this one. And then we have the next 4 bits, which is this one. So the first one here, just 1 second, my pointer is too small. So this, if we're taking this into consideration, this will give us 9. If we're looking at the next one, this will give us what? 3. If we're looking at this as well, this will give us 3. And then the next one would give us what? 12. So at the end of the day, if we are to write the equivalent binary, sorry, it's supposed to be equivalent decimal number, okay? So here we would get 12, 3, 3, 9 to the base what? 10. Please, you understand? Is it clear? Okay. All right. So you just try your hands on these ones as an assignment, but not an assignment to be submitted. basically an example for yourself. Okay. So the next thing I would want us to look at before we end this particular unit, which is unit 1, is to look at something we call the XS3 code, or the XS3 code. Okay. The XS3 code is another important binary coded decimal. Okay. It is particularly significant for arithmetic operations, as most of the time it overcomes the shortcomings encountered using the 8421 BCD code, where you have to add two decimal digits whose sum are what? 9. Okay. Now, the XS3 code for a given decimal number would always be determined by adding 3 to each decimal digit in the given number, and then replacing each digit of the newly found decimal number by its 4-binary or 4-bit binary equivalent. So basically, this here is what we mean by the XS3 code. So for instance, for the decimal number 0, its XS3 code will be 0111. Sorry, 0011, which means that we are adding 3 to that number. Similarly, when you move to 1 for a decimal number, its XS3 code in binary is what? 4, where you have 01001, 0100. Then similarly for 2, you have 2 plus 3, which will give you 5. So you have 0101. 3 plus 3 will give you 6. So you have 0110. Then you have 4 plus 3, which will give you 7. So you have 0111. Okay. Similarly, you have the same procedure from 5 to 9. So 5 plus 3 will give us 8. So its equivalent representation in binary. 6 will give us 9. So you have its equivalent representation in binary. And that will basically be what? 1001. 7 would now become 10. So you have 1010. 8 will now become 11. So you have 8011. 9 would become 12. So you have 1100, which means that 8 plus 4, which is giving us 12, and then the other bits are all 0. So basically, that is how the XS3 code of these equivalent decimal numbers are. Okay. So as an example, let's find the XS3 code for the decimal number 597. So for 597, the addition of 3 to each digit yields 3 new digit numbers. So it means that if we're taking it from the left-hand side, if we're adding 3 to 5, that would end up giving us 8. If we add 3 to 9, that will end up giving us 12. And then if we add 3 to 7, that will end up giving us what? 10. So at the end of the day, 5 plus 3, which is 8, is now giving us what? 1000. And then 12 is now giving us 1100. And then 10 is giving us 1010 respectively. So at the end of the day, when you put them together, you are going to get 1110 0 0. Sorry, 1 0 0 0 1 1 0 0 1 0 1 0. And that would be the XS3 code for 597. Please, do you understand?
Oh, yes, sir. Yes, sir. Yes, sir.
Okay.
You understand?
All right. Now, there is something we also need to have an idea of, and
The,
that is
there
yes.
is a. Please, what's the significance of the SS3 code?
So normally, the reason why we use the XS3 code is that in converting the decimals to binary using the 8421 method, in some cases, there is a likelihood to make a mistake because of the addition of zeros. So in order to avoid that mathematical errors, that is why we mostly would want to use the XS3 code, okay?
So, in a question, if I forget, let's say, to add the 3 to the numbers and then to find the code, is it wrong?
If you are asked to do what do we call it? To do the conversion using the XS3 code, then you are bound to do that. But if you are not asked, you can do it. You can do the conversion in any way,
With or without?
with or without it.
Okay.
All right. So you decide if you are asked, if the question is just posed to convert the decimal number, and it is not saying use the 8241 or the XS3 code, you can choose to use whichever you want. But when you are done converting it, it's best you note which procedure you used. All right, so for alphanumeric codes also, they are character codes, okay?
Okay.
They are binary codes used to represent alphanumeric data, that is alphabetical and numerals, okay? So here you have letters of the alphabet, numbers, mathematical symbols, and punctuations and all that. Now, there are two widely used alphanumeric codes. That is the ASCII and then the EBCDIC codes. Now, let me test your acronym skills a little. What is the full meaning for ASCII? Can someone tell us? So basically, ASCII is American Standard Code for Information Interchange. American Standard Code for Information Interchange. So take note of that. You can note that somewhere. Has anyone been able to remember what EBCDIC is? Or you want me to tell you that one too? Okay, so that one also is called the extended binary code or binary coded decimal interchange code. Okay. extended binary coded decimal interchange code. Okay. Now these are basically alphanumeric codes, and they are the two widely used alphanumeric codes in electronics. So when you move on to look at this table here, you see the table has both the ASCII and then the EBCDIC codes for characters. So for space, you would have the representation. You will see one is a 3-bit and then the other one is what? A 4-bit. When you are asked to represent a space using the ASCII code, you would have to put both the 3-bit and the 4-bit together to write the ASCII code for space. So similarly, it goes through, you have the exclamation, you have the inverted commas, you have the hash, you have the $sign, you have the percentage, the ampersand, the apostrophe, the open brackets, close bracket, asterisk, plus, comma, the dash, the full stop, the forward slash, and then from A to Z as well. They all have their various numeric codes. So kindly take note of that. So these are basically what we term as alphanumeric codes. Okay. And then you would have decimal equivalent of these alphanumeric codes as well. So just take note of that. So this brings us to the end of Unit 1. And there is an example here which I would want you to look at. And it says, refer to the chart there. Normally, if I would ask you any question in exams, and it would mean, or it will require that you write anything in relation to alphanumeric codes, I would definitely give you the chart, and you would be asked to write those codes. So for instance, here it says list the 12 ASCII keyboard encoder outputs for entering the message pay $1,000. So you see the code here. P has its own code. A has its own code. Y has its own code. Space has its own code. The $sign has its own code. The number 1, which is the decimal 1, has its own code. The decimal 0 has its own code as well. Okay. And then the full stop or the dot also has its own code. So this is just a basically an illustration of how you can represent alphanumerics using the ASCII or the EBCDIC code. Okay. So basically this brings us to the end of Unit 1.